We have a guitar string with a linear density, meaning a linear mass density, of 2 grams per centimeter. It's stretched between supports that are 60 centimeters apart. The string is observed to form a standing wave with 3 antinodes when driven at a frequency of 420 hertz. So the pattern looks like this. Since the supports are 60 centimeters apart, that's the section of the string that is vibrating. So the length we need, L, is simply 60 centimeters. So first we want to know what the frequency of the 5th harmonic of this string would be. Which harmonic is this? Third. So this is specifically M equals 3. So F3 is 420 hertz. So what would the fundamental frequency be?
Why? So the 3 antinodes you just count. I thought you don't count the last 2. You're starting and
M equals 3 corresponds to specifically having 3 antinodes. So if the 3rd harmonic frequency is 420, what would the fundamental frequency be?
140.
How do we find it?
Divide by 3.
Divide by 3. We know the 3rd harmonic is simply 3 times the fundamental. So the 1st harmonic will simply be 420 hertz over 3. So the fundamental frequency would be 140 hertz for this particular string. If you were to cause that string to vibrate at 140 hertz, you would get the 1 antinode only. Okay? So the 5th harmonic is simply 5 times the fundamental frequency. So 5 times 140, which is what? 700 hertz. So if we were to oscillate this string at 700 hertz, we would see 5 antinodes. Okay. Now granted, you'd have to have some mechanical device to do that. Questions on getting that far? Okay, the tension in the string. How tight is the string? We know the linear mass density. Now tension, being a force, we would expect to have units of newtons.
Okay, is it the tension of the string originally, or the tension of the string of the 5th harmonic?
The tension of the string is the same.
Oh, it's the same, yeah.
Yeah, so the tension is the same regardless of which harmonic. What we've changed in terms of the harmonics is just how fast we're oscillating the string. So there's something mechanical holding onto one end of the string and vibrating up and down, causing it to vibrate.
Could you also like hit it with really loud sound to get it to vibrate?
You probably could, actually. If you get just the right frequency, you could get the vibrations, the antinodes, yes. Tension. Tension needs to be in newtons. That's the SI unit for force. Remember tension, not tension, but newtons. Newtons is a kilogram meter per second squared. So I would highly recommend getting this in kilograms per meter before heading onwards. So we have 1,000 grams per kilogram, 100 centimeters per meter. So this would simply be 0.2 kilograms per meter. So we know the linear mass density. We now know the fundamental frequency, the 3rd harmonic frequency, the 5th harmonic frequency. So speed. Speed of a wave on a string we know is equal to the square root of force of tension over the linear mass density. But we also know that the speed of a wave is also equal to its wavelength times frequency. We could use the wavelength of the fundamental times the frequency of the fundamental. We could use the wavelength of the third harmonic times the frequency of the third harmonic. Or wavelength and frequency of the fifth harmonic. You just have to be consistent. If you want to do them for the fifth harmonic, you have to know for the fifth harmonic for both. Doesn't really matter which one we use. Do you care? Okay. Let's use the original info. So let's use the third harmonic. So we're going to find the wavelength for the third harmonic and frequency for the third harmonic was given. So the force of tension, when I square both sides and bring mu up, that's going to be the force of tension. So lambda 3, the wavelength for the third harmonic is going to be 2L over 3. 2, L is 60 centimeters, so I would put that into meters, so 0.6 meters. 2L over 3 is the wavelength. We need to square that whole thing. The frequency for the third harmonic was given, that's 420 hertz. We need to square that as well. And then the linear mass density, we've just changed to kilograms per meter. So plugging and chugging from here. Oops.
So a Newton is a kilogram meter per second squared.
Correct. So we have meters squared there, which is going to cancel with one of those. We have our kilograms there. So we have kilograms, meters. Hertz is 1 over seconds. Once we square it, that's where we're going to get our seconds squared. So, really big tension. So I'm assuming our string is capable of withstanding that.